Hello, everyone. Thanks for joining. My name is Ben McDonald. I'm the lead engineer of the Arkouda project at Hewlett-Packard Enterprise. And today I'm going to be walking you through some information about Arkouda, starting with kind of a quick sort of sales pitch, getting you on board of why you would want to use Arkouda, and then walking through a demo with a GitHub code space. So this talk is called Data Science Beyond the Laptop, Handling Data of Any Size with Arkouda. And these slides were prepared with by myself and then some help from colleagues, Michelle Strout, Sarah Coughlin, and Oliver Alvarado Rodriguez. So let's get started. Okay, so when we're talking about data science, I think today that, you hear that term all the time. It is a really big buzzword, and I think it can sometimes be easy to get lost in what that word actually means. So throughout this talk, the way I would like you to think about data scientists are to think about data scientists as modern day explorers, uncovering previously unimagined insights. Where I think the analogy here is useful because if you imagine explorers back in the day, they were able to come to new places, like come to America and find all of these new areas that people hadn't really been before. Now data scientists are kind of doing that same sort of thing with data. They're coming into these data sets and finding new kind of insights that nobody's ever imagined before, just like the old explorers. So that's how I'd like you to think about data scientists throughout this talk. And so one of the problems that both data scientists as well as explorers from antiquity have suffered from is something called the lighthouse effect. And so what the lighthouse effect is essentially this idea that like you can only see what is like illuminated to you. If something's not in the light, you won't be able to garner insight from that data. So yeah, so that's just a way of thinking about data sets. Like if you can't view a data set in its entirety, you don't really know what you're missing. And so just like a explorer without the illumination of a lighthouse wouldn't know where they were going. Data scientists face a similar problem if they don't have an illumination of the entire data set. And so the question that we are asking and trying to answer with Arkouda, and I believe we've answered with Arkouda, is what if we could work with massive scale data in its entirety without compromising interactivity? And so thinking about that lighthouse effect, it's like, what if rather than having to do something like downsample the data, we could view the entire data set, work with that all at once, and then be interactively learning along with our data set rather than having to take a smaller subset of that data and then be subject to that lighthouse effect. And so just to kind of show you some of the impact that we've had with Arkouda, here's like a quick performance graph that was gathered in May of 2023. And this was performance gathered on a Slingshot 11 network where we were able to get up to, we scaled pretty linearly with Arkouda ArgSort up to about 8,000 nodes, where we reached close to 9,000 gigabytes per second. And so this was on 256 terabytes of data. And so we sorted close to 10,000 gigabytes of data in about 30 seconds. So I think this was a really cool accomplishment. Like if you see on this graph, in the runs leading up prior to this, we only had ever had the chance to go up to about 800 nodes in Arkouda's runs. But then when we got up to this larger machine and had the opportunity to run to 8,000 nodes, Arkouda scaled linearly up to that point, which was something I was really, really proud of and impressed to see some of the works of my colleagues go into that. Okay, so now that was just like a quick introduction of like the type of problems that we're trying to solve with Arkouda. And so now I wanted to jump into kind of talking about some of the demands of data science today, and then talk about what is Arkouda at a more fundamental level, and then talk about Chapel, the language that Arkouda is built on, before wrapping things up and then taking it to a tutorial in a GitHub code space where we'll all get to actually run some code. All right, so today, data scientists, if you are a data scientist yourself or have talked to many data scientists, it's a very common theme that data scientists these days are using Python. And one of the big reasons for that is the interactivity that you get in Python. And so this interactivity comes from the Python REPL, the read, evaluate, print loop model that Python is built on, which essentially means that, yeah, it's just essentially interactive code. You don't have to wait for any compilation. You just enter a command, it runs, and then you can run another command based off of that result. And so along those lines, data scientists also have come to expect that operations in Python will complete within the human thought loop. So that means like before you totally forgot what you were doing, your operation is going to spit you back a response. And then that enables kind of that interactive learning along with your data, where you can be learning as you go. Like you learn from a command, then that leads you to make your next command. And so that kind of roundabout way of saying what I was saying there is kind of just that data science demands interactivity. Like in order for a data scientist to make those kind of insights that are needed as a data scientist, you need interactivity in the code that you're writing. And that's what Python has provided for data scientists so far. And so one of the things that I mentioned there is that this code is expected by data scientists to complete within the human thought loop. And so when I think about Python, and I think like a common stigma of Python itself is that it's a rather slow language. So then I think that leads to the question of like, how do we then get these data science libraries that are performing well? And the answer to that is that data science Python is only syntactically Python. Like when you run something like a NumPy function in Python, you're not really running Python code. What you're running under the hood is something like you're running like a precompiled like C or a Fortran code that's going to execute very fast, but you have this Python front-end interface to it that allows kind of this connection between performance and interactivity. So it provides the performance of C with the interactivity of Python. And so this is just kind of like a typical model of how Python packages are developed, and just highlighting that data science Python isn't really Python code that you're writing. It's more of like a smorgasbord of a bunch of different languages that is syntactically Python to help with the user experience of that code. And so the next point I wanted to make here about what data scientists are expecting today has to do with data size. And so as I'm sure all of you are aware of, data sets have outgrown typical computers today. It's very common that you're working with like a several terabyte data set or a petabyte data set. For example, if you're loading in just any sort of huge data set these days. And then once you get that huge data set, there's been kind of like this approach of unbiased sampling is kind of like the gold standard of how you can work with those giant data sets in memory on your laptop or whatever machine you have access to. And so this unbiased sampling approach, you essentially like take your huge data set, you try to pick out pieces of it that's going to give you like this unbiased sample so you can accurately assess the data. And then from there, you work with it on your laptop and just kind of hope that you're working with an accurate data set. And so a few notes about that unbiased sampling that I've mentioned is unbiased sampling is something that is very difficult. Like you never really know if you're getting a perfect like unbiased sample of your data set. And yeah, so you never really know if you're getting a perfect sample of your data set. And beyond that, like we have this problem of unbiased sampling eliminating rare and high order effects. And so you can think of that as like, imagine you have a huge outlier, like say you're looking at the amount of money that people spend on airfare every year or something like that. If somebody has their own private jet, that's going to be a hugely like rare and high order effect, but it's an important piece of that data set that unbiased sampling will typically not be able to accurately take into account. And so, yeah, the point that I'm trying to make here is really that data science demands scalability. Like this unbiased sampling problem is not a perfect solution. And if we could read that, like if we could have the complete picture of that data set, that really would be the perfect solution that data scientists are looking for. And so just to wrap things up here, the point that I'm trying to make is in order for Python to be useful to data scientists, we must have Python that scales beyond the laptop but that does not sacrifice interactivity. So we're able to work with large data sets. We're still able to complete operations within the human thought loop. We're still able to run interactive operations. And so that is the goal of what I mean, and that's the design and impact that we're hoping to make with Arkouda. And so on this slide here, this is just kind of like a high level look of what Arkouda is and how we provide this interactivity and scalability elements within Arkouda itself. And so how it works today is we have this Arkouda client that's written in Python where you could have something like a Jupyter notebook running on your laptop, interacting with that like you would any other Python library like NumPy or something like that. And then the scalability is provided in the backend by our Arkouda server, which is written in Chapel. And this Arkouda server can be ran anywhere from your, like it could be run on your laptop, it could be run on a supercomputer, it could be run on a cloud, really anywhere that your machine is able to connect to, like has access to the server on. So, so in that sense, like once we have this Arkouda server that's scalable and running on like a supercomputer or something, from the Arkouda client, you'll be running commands, and that will send messages to the server to execute that code and take advantage of that larger resources that you have access to, and then communicate kind of like a machine, I mean, not a machine understandable, a human understandable response back to the Arkouda client. So our data scientists can keep doing their interactive data analysis and keep learning along with their data set as they go. And so just kind of like a summary side of Arkouda here. So what Arkouda is itself is an open source Python package that provides interactive data analytics at supercomputing scale. And kind of like the tagline that we've come up here is transform the way you work with big data, massive computation within the human thought loop. Just a few more points I'll make here about Arkouda before moving on to some information about Chapel is Arkouda itself is easy to use for a data scientist. It provides an API data scientists are familiar with based on pandas and NumPy. And it's also fast and scalable, like you saw in that initial graph that I showed, where we were able to sort 256 terabytes of data in about 30 seconds. It's extensible and customizable. Like there's a highly extensible ecosystem that allows rapid feature development and broad project collaboration. And I would also note that there's kind of there's a pretty broad ecosystem right now. There's a lot of different groups working on in Arkouda and Arkouda adjacent technologies. And so that really just highlights this extensible and customizable element that I will come back to a little bit later in the talk. And then lastly here, Arkouda is powered by Chapel, which is the parallel distributed server that's running in the backend. And so this talk itself was originally given as a part of ChapelCon. So if you were attending from ChapelCon, you probably already know what Chapel is. But if not, I've got some information on Chapel itself as well. And so what Chapel is a new parallel programming language, depending on how you define new. And so Chapel is, like the tagline we have here is, from laptops to supercomputers, Chapel makes parallel programming more productive. And so if I were to characterize like the high level goal of Chapel, it's like to provide a Pythonic-like syntax and abstract away a lot of those like difficult parallel programming and distributed programming concepts that have traditionally been pretty intimidating to new developers and not something you really learn in school. So Chapel's kind of trying to bridge that gap between what people are learning today in school, like Python or C or something like that, and then bringing that up to parallel and distributed programming in a simple way. And I'm sure some people on the team would not be happy with that characterization, but that at least is how I would think about Chapel as an engineer on the team. And so we've kind of got a number of notes here. I won't go into all of them. But like some of the key features of Chapel are it's fast and scalable. You're able to scale your applications with ease. You can run from your laptop. You can write code on your laptop and run it anywhere from like, you can run it anywhere from your laptop to the cloud to the supercomputer, like I was talking on the last one, on the last slide. And this is like code that you can write on your laptop without making any changes to it. And it just looks like regular code like you'd write in Python. That really works anyway. And then Chapel also has GPU support that has got a lot of excitement lately. We don't today support a lot of GPU functions in Arkouda itself, but we do have some work going on there. And lastly, Chapel is open source and can be viewed on GitHub if you are interested. Okay, so that was kind of the quick sales pitch summary of Chapel and Arkouda. And so now just to kind of like revisit this Arkouda model to really try to cement this idea in your mind of how Arkouda is working under the covers. And so just to reiterate, when you're writing code with Arkouda, what you're writing is Python code. Like it should look no different, and it does look no different than your typical NumPy code, where you're writing in a Jupyter notebook, you're getting those human responses, and you are just learning along with your data. And so when you write some Python code that makes a call to the Arkouda library, what's happening under the covers is you're passing data from a ZOMQ socket that's telling the server that the client has requested to run this command. And then from there, we come to this Chapel server where we have our dispatcher, which gets the message, parses the message, and then kind of like determines what it is to call, like calls that function, and then creates the array in like a distributed object. I mean, in this distributed object store that we have in Arkouda. So you can imagine if you, from the client side, you tried to read in a giant like multi-terabyte data that wouldn't fit in Python, like your client memory. This would come to the server. It would read in that huge file, all on the server side of things, all distributed. So that way you could store that large file in this distributed object store without having to worry about the amount of memory available on your client. This is all handled on the server side of things. And then from there, your Python client is going to have essentially like a just like a pointer, you can think of it as, to your Chapel server side memory. Whereas like if you query that pointer on the client side, it's always going to be communicating back to the server and then getting kind of like a human understandable response to get back to the user, rather than trying to pull the entire array back into memory, which you can do, but that's not how most operations will run by default. Okay, and so I mentioned before that we kind of have this Arkouda ecosystem where Arkouda itself is pretty extensible. It has this sort of modular build system that allows developers to write new code and easily like essentially drag and drop that into the Arkouda package to start using that code, to start using that distributed parallel code from your Python interface. And so one of these really exciting packages I wanted to call out is this project called Arachne, which is coming out of the New Jersey Institute of Technology. And what Arachne is really like the GraphX of Arkouda. Like it's like a parallel distributed GraphX. And so we've seen some performance results come out of Arachne versus GraphX, where like I don't have the actual numbers here, so I'm hesitant to say, but I know I've seen numbers about like 100x faster with Arkouda and Arachne over GraphX. So that's some really exciting work that I wanted to call out here. And so what Arachne does, I mean, I know that was a very vague description, is like, so you read in some data or like just create like a large distributed graph or something like that. And then you're able to, Arachne provides you kind of like these parallel and distributed graph algorithms like breadth first search or subgraph isomorphism or something like that. So you can be working on gigantic graphs from your laptop in a Python client. Okay, so I know that was kind of a lot of words spit out all at once, and so just to kind of summarize everything that we've talked about in this quick introduction of Chapel and Arkouda, is that data science requires an intimacy with data that's reached through interactive exploration. And regardless of data quantity, quality requires scalable workflows on the complete data set. And that's going back to that point. Like we can't downsample our data for certain applications. Like we need the entire data set in the cases where we need that. So that kind of is the goal of Arkouda. That's what Arkouda is trying to solve. This is what Arkouda provides to its user, is scalable interactive data science for data scientists. And so, yeah, so that was most of the material I had prepared for this initial like introduction to Arkouda. And the next thing I wanted to walk you all through is an actual tutorial of Arkouda that I presented for that ChapelCon this year, that we will go through this Arkouda code space that we have. Okay. So I will be walking through this live in a sense while we are going through this. So that means that you all should be following along now and go to this repository. There'll be a link in the description to where you can get to this repository, and I'll be showing you how you all can do that from in this tutorial. So from this repository, if you come up to the use this template and say open in a code space, then this will launch a GitHub code space where you'll be able to actually get in, get under the covers and start running some Arkouda code. And so what a GitHub code space is, it's essentially a cloud development environment. So we have this Arkouda Docker container that is this repository is essentially pointing to. And then when we create this code space, it'll load up that Docker container, it'll start your Arkouda server, and it'll start a Jupyter server. So you can be running, so you can connect to that Arkouda server from your Jupyter notebook and be running the code from there. So that is the idea behind this, this GitHub code space. And so now we've got kind of this awkward time here while we're waiting for it to finish up. So just to reiterate, you really should go and try out this GitHub code space and running code yourself if you haven't. So you've got no excuses with this silence here. Yeah, so while this is loading up, like I will just go through over like a quick kind of talk about what we're going to be talking about in this tutorial today. So like just to start it off, we'll be talking about like how to use Arkouda, how to like import the Arkouda package, launch a server, connect to a server, and create arrays. And then after that, we'll be talking about the Arkouda API and some of the things that are some of the things you can do with Arkouda, and all this is going to be through following like a real life kind of workflow using the New York City taxi cab data that's available with open access online. So that is what we will be covering in this tutorial today. All right, look at that. We are get started here. So now that our Arkouda code space is up and running, like we're gonna see like it still isn't quite ready yet. We're going to be having our Arkouda server and our Jupyter notebook getting started up here, which should happen automatically here. Just and so when these do start, we'll see some ports show up for our Arkouda server and Jupyter server. So we will just give it a minute here. I don't know why this is not starting. It should have. Okay. Okay. I had to manually run the startup.sh file. So this is showing, you might run into some issues along the way, but you got to work through those. That's one way you can do that. So so now I ran just like I launched my like startup.sh script, which just runs a setup file. And then now you can see here we've got our Arkouda server started up on port 5555. And here we have our Jupyter notebook started up on port 8888. And so now we have these forwarded addresses here. If you go to the Jupyter notebook one and click on this kind of globe icon, I guess that would be, then that will open up our actual GitHub, our Jupyter notebook where we can start working with some of this Arkouda code. All right, so here's the files we have in this repository. The one I'm going to be working from is this clean tutorial New York City taxi parquet file, which is a mouthful in hindsight. I should have, yeah, but okay. And so, yeah, so this is, I kind of talked about what we're going to be talking about a little bit here, but so kind of the steps that we're going to go through this in this tutorial are we're going to connect to our Arkouda server. We're going to read in that parquet taxi cab data. Then we're going to do some data exploration on that data where we look at some descriptive statistics, do some plotting with histogramming and some logical indexing. And then finally get into some of the more advanced features of Arkouda by creating a lookup table and data frame. And then finally talking about how we can use Arkouda to work with NumPy and pandas, which is typically what our data scientists will do with Arkouda. Like they will work with this Python data set. They'll kind of understand all the physics of that data set as it stands on the full data set. And then once they understand the data set, they'll get down to this smaller working set and push and work with that smaller, like convert that to the server, to the client, and then work with NumPy and pandas like they would any other workflow. And so that sounds similar to the downsampling model, but what's different about this is that you're starting with an understanding of the data set rather than trying to do this unbiased sampling on a data set that you don't really understand. Okay, so that's enough of me just talking. Let's get into writing some code. And so the first thing that we're going to do here is we're just import Arkouda as AK like you would with any other Python package, and then connect to this server with the ak.connect command. Why is this not running? Okay, there we go. So we'll see this cool Arkouda splash art here with the Arkouda logo, or not logo, just says Arkouda. And so now we see that we are connected to the Arkouda server, which means our client has established a connection to the server. And now any commands that we use to use that come out to this Arkouda library will be communicated to the server and running things on the supercomputer essentially, which isn't a supercomputer in this case, but is in practice usually. And so now here are just some imports like pandas, NumPy, matplotlib, and the garbage collection to highlight some things along the way. And so the first thing that we're going to do here is actually read in our Parquet taxicab data set. And so this green trip data from January 2024 is included in this repository. So if we read in that with this has non-float nulls value for some compatibility Parquet kind of specifics, then if we view that data, we see that we've read in our data set. And so if you look at this data set, or actually, let me run these next two commands before I do that. So here's kind of like a more like converting this data set to a data frame to get a little bit nicer view of things. And then finally, like if we print out like the number of rows in the file and the number of columns in the file, we'll see there's 57,000 rows in this file about and 20 columns in the file. But if you look back at like this initial representation of the data that we had, what you're seeing here is you're only seeing like 6 values represented, like the first 3 and the last 3 for each column here. And so what the reason for this and like is due to this Arkouda like client server model like I was talking about. So this data doesn't actually live on the client side. Like the Python client doesn't actually know about this data. What the Python client has done here is queried the Arkouda server, told the Arkouda server to read in this data set, create a distributed array on your distributed object store, and then return to me some way to point to that data from the client side. So when we then query the server to say like, just like print out this data set, so let me view my data. What the server side is going to do is going to send back these like human readable representations of the data rather than the entire data set itself. And so this is really just like a string response that was gotten from the server, like the first 3 and the last 3 elements. So someone can view that, make sure it like makes sense and looks good. And then, and so we worked with that without having to pull back like we're able to view the data without having to pull it all into memory on the client side. So if you were running this on a supercomputer, it was way more memory than you had on your laptop. That is how Arkouda gets around that problem. And so, yeah, this is just highlighting Arkouda's data frames and what we'll be using to view our data throughout this tutorial. And so you'll see that in this, we kind of have some information like the number of passengers in the ride, the trip distance, the fare amount, the tip amount. Yeah, so just kind of information on these taxi cab rides. And so I guess I don't think I've actually really described what this taxi cab data set is. And so this is kind of like New York City publishes their taxi cab data each month. And it's essentially like for all the taxi cabs in New York, where just like provide information on those, like each ride, like where are people traveling from, where are they going to, how much did they pay, and that sort of thing. So that's what's represented in this data here. All right, so moving on there from some into some data exploration stuff. So Yeah, so I guess this is kind of just talking about that PD array function, like stored on the server I was just talking about. And then I guess like the other thing that this is reminding me to highlight here is that Arkouda's interface is based off of the NumPy and Pandas APIs, which I think I've kind of alluded to before. But it really should feel, just do data science, exactly like you're running NumPy and Pandas code. And there's actually an effort going on in Arkouda right now to align them more aesthetically perfectly, I suppose. I don't know the exact term, but we're hoping to get to the point where you can just replace your like import NumPy as MP calls with import Arkouda as MP, and then your code should just work from there, is the idea there. Like there's going to be perfect alignment between the APIs is the end goal. And so along those same lines, we also do have support in Arkouda for the array API. I think we're about like 95% of the way there, where there's some device-specific stuff that we aren't planning to, at least not in the short term, to provide support for in Arkouda. So if you're familiar with the array API, I won't go into a ton of detail into that right now, but if you are already using the array API for some of your workflows, Arkouda should fit into that workflow as well. And so, yeah, from there, I will start getting into some of the actual descriptive statistics, some of the code you can write with Arkouda, and what kind of things you can do with Arkouda, and what we learn about this data set. And remember, we're explorers going about this data set. It's been a long time since I've looked at this, so I'm going to be learning along the way with y'all here. We're going to be doing some real data science here. And so what we have here is a function that we've just entitled describe. And so what this describe function does is it gets the mean, the standard deviation, the minimum, and the maximum of each value of each column. And so if we run that across our data set, what we're going to see there is the mean for the fair amount is, on average, people are paying $17. The standard deviation is 15.36. The minimum value is -$70 somehow. And the maximum somebody ever paid was $1,400 for a taxi ride. So yeah, that's just kind of some summary statistics on the data set. During the live tutorial, we had some people in the audience chipping in, potentially saying that maybe this minimum value was sort of one of those cash cab sort of things. And we're talking about the maximum value as well, but not as many ideas there. And so, sorry, I have been saying a lot of words real fast. So, all right. From there, now we're going to visualize some of this data through some of Arkouda's histogramming functionality that we have. And so what we're doing here is we are creating this Arkouda histogram, just like how you would with matplotlib and NumPy sort of things. Like create your histogram before plotting that with matplotlib. And so what you'll notice here is while we are passing like this, we have like our full data set here represented by this X, and then we're calling this histogram function to get back like our number of bins and the binning itself. And so we're not actually going to have to pull back the entirety of the data set in memory for this. Like we just have this smaller representation of the data. So that's why this is kind of like a reasonable command to run in Arkouda, is like histogramming and working with matplotlib, is because you don't need to actually localize the entirety of the data set to your laptop, which would be much too much memory for your laptop if you were running this on a large data set. And so now if we actually plot a histogram of this data from the fair amount, what we're going to see here is it's pretty normally distributed around kind of like this, I don't know, maybe $50 mark, where we have kind of like this portion of the data that is negative for some reason. And then this one guy who paid just like 3 times as much as everybody else at the maximum. Like, I wonder, yeah, there's some interesting questions you could ask about that guy. But yeah, so that's kind of like how you can get Arkouda to interact with matplotlib and plot some of that data. And so at this point, there's an exercise here to inspect that expensive fare outlier, where I had forgotten about this. So let's see if my data science skills are still up to the task of completing this exercise. And so the idea here is to index into your data frame using logical indexing to inspect that expensive outlier ride. Like get the information on that expensive outlier to see if we can learn some more information that's going on there. And so there are a few different ways you can do this in Arkouda. We have kind of like an argmin and an argmax function where you could get the index of that maximum value of the fair amount and then index into the PD array and get the result there. But here, just since I haven't introduced that yet, I'm recommending to do something more akin to this. And so I will give you all a second to try to finish that before solving it myself. But just in 1 second, I will give away the answer here. If I'm able to do it, that is. All right, so I think what we want to do here is, so we're using our logical indexing. We have this data. We want to get the largest fair. So we go, so we want to get the largest fair, but we're not going to use argmin yet because I haven't introduced that in the tutorial proper yet. So I'm recommending these logical indexes. So if we do a data fair amount that's greater than $1,000, like we can see from this visualization of the data that there's really only this one data point. So we know that this is going to get us our single value there. And so if we print out that, oof, I got it right. That was some nervous there. But so now we've got this kind of expensive data set, this expensive fair ride that we can analyze here. And so what we can see here is, like, we look at this, we have a lot of information that doesn't make a lot of sense just looking at it. We have this pickup location of 92, this drop-off location of 265, and that doesn't mean much to us now, but it will later on in the ride. What we can see is there was 2 people on this ride. They traveled about 35 miles, so they paid like $40 a mile. I honestly have never ridden a taxi in my entire life, so I don't know if that is I don't have a good sense of if that's expensive or not, but judging on this ride, like compared to the others, it seems very expensive. You'll notice here they left no tip. So they had this extremely long, extremely expensive ride that was not deserving of a tip. I mean, I'm sure there was a reason for that. It sounds like it didn't go too well based on the comparison of this ride to the others in the data set. So this is us doing some real data science here. You know, this is the life of a data scientist, going through and actually learning through your data set. Okay, so the next thing that we're going to do here is we're going to do some data cleaning. So like I've kind of been talking about, we have these weird spares that are like less than $0. Like, you know, like we have this -70 minimum ride. Like that doesn't really make sense to me to look at as a ride. So here what we're doing is just going back to our data set and getting rid of those negative values to clean our data set and only be working with ones where people actually paid, they didn't get paid for their rides. And so what we're doing here is a logical filter of our fare amounts, all fares greater than 0. And then we're going to print out the number of non-negative values divided by the total number of values to get the number of fares that are non-negative. So what we'll see here is there are 99.7% of the fares are non-negative, meaning there's just that small portion of them that are. And so now if we run that command again to describe this data without those negative values, what we're going to see here is our mean has jumped up to $17, where before it was 16.93. So our mean went up 8 cents from removing that. And then, yeah, so our minimum is now at 0 and our maximum is still that large $1,400 ride. Okay, so now I've gotten us to our second exercise that I also have forgotten about, where we are trying to check out only the negative pairs, to inspect only the negative pairs, where here we were inspecting the non-negative pairs. Now we want to inspect only the negative pairs and get some information on that. So I won't leave the pause for you all to solve this one this time. I will just go ahead and try to answer this one for us all. So if we have, so coming back to this, we have our negative pairs are all our data where like each fair amount value that is less than 0, that should give us our negative values. And then from there, so this negative should be all the fares that are less than 0 fair amount. And then if we describe that, if we describe our data set, I will just copy and paste this one again. I don't know why I'm trying to type this out. Typing on live is not fun, but okay. So now we're going to do the same thing except on the negative values of the data set. So what we're doing here is we're like indexing into our data set at fair amount and then applying this filter for all the negative values. So if we describe that, what we'll see here is the average like mean fare was about -$8 here. Where somebody, the most somebody got paid was $70. The least somebody got paid was 12 cents. So if this is that tax cab example, cash cab, I think it was called example, then this guy did very poorly and only made 12 cents on his ride. All right, so I made it through those two exercises. I'm very proud of myself. I'm not a data scientist. I'm an engineer, so I'm mainly working on the implementation of these things in the back end rather than the front end kind of thing. So this really has been a learning experience for me as well. All right. And so now what we're doing here is just coming back and kind of building out a data frame with our data, like only with the non-negative values here. So here, yeah, we're coming into our data set, getting all of the non-negative values, and then replacing that with our data set to filter out that data. And so now you'll see we're down to 56,000 rows, 56,369, as opposed to this 551. So that's 182, I believe, removed from our data set from this data cleaning. Okay, so that was probably a bit messy, but I made it through that one, so we're moving on. And so now we're this next part here, what we're going to look at is what I was talking about for how we can get Arkouda and pandas and like other Python libraries to work together to make things that work, to make things that work. I'll go with that. So what we have here is we have this CSV file that we want to read in with data frames, with pandas. And what this CSV file is this taxi zone lookup table, which we will, maybe I should run this code first and try to explain it after that. So what we have in this taxi zone lookup table is essentially these location IDs, which we were looking at in some of those previous examples. And what this is doing is it's like pairing some of this data that we had in our initial data set, like these location ID numbers that like don't mean a lot, just looking at them. And then it kind of pairs these locations with an actual physical location. So like, for example, location 1 is this Newark airport. Location 2 is Jamaica Bay in Queens, and like 265 is outside of New York City. So these are just like connecting these numbers to a real, real human understandable response. And so like when in data science, when you're doing something like this is called like enriching your data set. So what we're doing here is we're using pandas and the pandas like read functionality, like CSV reading functionality to enrich our data set. So what we do here is like we read in, we construct our like conversion, construct our conversion function here. We read in our lookup table into pandas read CSV function with these converters. And then from there, and so from there, we now have this like lookup table read in pandas. And so now we can like come in to like Arkouda side of things, get this pandas data frame to Arkouda data frame. So that way we can enrich our data set and make each column have these representations of like these human understandable representations. So as a data scientist, we can look at the data and garner more insight from it as like a human readable response rather than just like numbers and tables and that kind of thing. And so if we call this Arkouda like create from data frame function here, which essentially all we're doing is like just calling this from series method and on our pandas data frame, and then creating a Arkouda data frame from that. And so now if we print this like Arkouda lookup table, we now have this we now have this data set converted to Arkouda. So that's how we converted this pandas data frame to an Arkouda data frame to get those two to play together. And so now that we have gotten our data frame into Arkouda, we can start actually enriching our data set and like putting back some of those rows into our data. And so what we're doing here is we are going into our like Arkouda lookup table at the location ID. This first one is not doing that much. I should have tried to understand the full thing first. What we're doing here is just making sure this is like a zero up index table, like a dense index. Essentially, that means like we just want to make sure this has every like value from 0 to 265. That way, we're not like doing any bad indexing with the data set that could cause an error down the line. Okay, so now we're getting into the actual data enrichment. And so what we're doing here is we're going back into our initial data set, and we're going to be adding this pickup borough row or column, I can never remember. We're going to be adding this extra like piece of information to our data set for a pickup borough and a drop-up borough. And how we're going to be doing that is like going to our lookup table that we've just created here, get the borough, like get the actual like neighborhood, the real place that it's from, and then index from that, like based off of the pickup location ID. So essentially, like if our data set says pickup location 0, then we want to, or like I guess pickup location 1 is a more interesting example. Then we're going to go into our lookup table, and then use our data's like location ID to pin this like actual borough, so like EWR in this case, to our data set. So that way we can make some more sense out of our data. Man, I'm sure that didn't make any sense, but this is going to lead to us making more sense. So, okay. Now that I have said all of those words that didn't mean very much, if we look at our column, this like to kind of put that into an actual like understanding, what we have here is like we've essentially appended on these 4 extra rows to our data set. So now we have like this pickup borough, drop-off borough, pickup zone, and drop-off zone. And so these now have like a little bit more interesting information than we were getting with just the numbers previously. So now we know like this ride came from Upper East Side North and was dropped off on Upper West Side North. So if you live in New York or you know anything about New York, these might mean something to you. I have no idea what any of these mean, but they mean more than just the numbers I was looking at before. Okay, so we now have enriched that data set. It looks like this is some code that I wrote that slipped in here by mistake from a previous run, but this is coming back to that huge negative ride just to get some more information on them now that we've enriched our data set a little bit more. And so what we'll see here, like now looking back with these extra information here, it looks like he was picked up in Queens, New York, and then he was dropped off outside of New York City. So that doesn't provide us a ton of extra information. He could have gone anywhere that's not New York City, essentially. So we know that he went from Queens to outside of New York, and for some reason that cost $1,400. So I shouldn't, yeah, it was these 2 people. Okay, so now moving on to like talking about some of Arkouda's more advanced features with a group by and like constructing a graph here. And so what we're going to be doing here is defining a graph from our pickup location ID to our drop-off location ID. So essentially what that means is like we want to get all of the rides that are picked up from the same spot and dropped off at the same spot. So like, for example, in this case, we want to get all the rides that are picked up in Queens and dropped off outside of New York. And so that way we can do some more specific analysis on that subset of data. That should provide us some more interesting insights. And so, yeah, so I guess like the other thing I'll mention here is like really the key feature of Arkouda that we've heard is like what makes Arkouda valuable, and we know that is why our users are essentially using us, is that Arkouda's like sort, which is used by group by under the covers. And so Yeah, so Arkouda sort essentially has like really good parallel scalability and performance, which so like what that means is if large sorts are a bottleneck, Arkouda is likely a great option. So if group bys are a bottleneck, Arkouda is a great option for that type of workload typically. Um, yeah, okay. So now from there, I will actually start to run this group by to show that it actually works in Arkouda. So here we ran our group by, grouping all the pickup location to drop off location. And so now if we print out our unique keys here, what we're going to see is essentially like the indices that you would use to get these groups from your like new group by object that we created here called byloc. And so how we were indexing into like our values previously was we were using something like the fair amount to index into our values, I mean, into our data set to get a specific row or something like that. What we can do now with this group by object is use these unique keys to get kind of like these groupings of objects. And so like if you look at what we're seeing here is we have like this unique key is like 1 and 1 here. That means like when we index into this group by object, we have to use these two values like 1 and 1. And then that will be returning us a group of rides that we can analyze as a set to get some more insight on like all the rides from like, you know, in this case, all the rides from Queens to outside of New York. And then through that information, we could see like, yeah, maybe this was a huge outlier for all the rides, but what about specifically in Queens outside of New York? Like, is this more of a common trend or something like that? So that's how we're using this group by object in this case. And so just to kind of like show this graph feature that we have here, we're calling this byloc.size function, which is returning like all the edges for the vertices and the number of occurrences of those edges. So in this previous example, I recognize I'm starting to talk too fast and not make a lot of sense. But so what we're seeing here, we're printing out the edges, the vertices are like UV, the pickup location and the drop-off location and the number of occurrences of those pickup location and drop-off location. So so that means like in this group where somebody is picked up and dropped in pickup location 1 and dropped off in pickup location 1. Oh no, our kernel died unexpectedly. Uh-oh. Well, hopefully things just keep working. Let's see. Okay. Okay, sorry, I'm having to. Sounds like our code space died. Okay. Sounds like our code space died. No. Okay, we're gonna have to restart our code space there. But so we actually don't necessarily need our code space. I feel like you all have seen that this stuff is running and that you've gotten the feel of Arkouda running. So I don't know if actually running the code is providing a ton of value. So luckily I have gotten this pre-ran example, which means I won't be able to go through the exercise with you all. You're gonna have to figure that one out yourselves because there's one more exercise at the end here. And so as I was saying, this like edge, like, man, I don't know, edge and vertices, like the pickoff location, the drop-off location, there's 3 rides that fit into this group here, essentially. So like that's all that's being shown here. I don't know why I'm spending such a large amount of time on that. Okay, so this next piece here is something that's a little bit more unique to Arkouda, which is called broadcasting values out, where we're going to like essentially with something like the data enrichment that we did before, you took like this data set, you took this piece of data, you put it and you applied it to, you took this like extra information and you applied it to your entire data set. But what we're doing here is we're taking something from our group by object and broadcasting that back out to all the values that match this particular group in Arkouda. So it's like, if you wanted to get the mean value of like this entire of like each group in here, this will now like attach the mean value of the associated group back to the original data set. And so that's what's being done here. And so now that we've broadcasted these values out here, you'll see we have an additional 2 columns. Now we're at 26. And so what you'll see here is like now we have the mean value from each group that this is in. So like this is the mean from each pickup borough to drop-off borough. So people who are going from Manhattan to Manhattan, it averages about $13. And this ride is like 3 standard deviations away from that average value. This one here is 22 deviations away, but okay. That is what was being done there. Lastly here, what we're going to be doing is calculating a z-score, which I think like that is like actually like the number of standard deviations away you are from the mean. And so if we've calculated our z-score, we do a histogram on our z-score. And what we're going to see here is this is actually like remarkably standardly distributed, where we're seeing like the kind of this even like slope from each, like cheaper rides to more expensive rides, where we have a couple more expensive outliers here as well. All right. And so at this point, this is kind of like doing what I was talking about in the start of this tutorial, is where we're bringing this small result set back to pandas. And so like we've explored our data, we've discovered our insights, like we looked at this entire data set, we figured out what we needed to learn. Like we figured out this guy paid $1,400 for a ride, and that isn't like a huge outlier that likely wouldn't have been caught by the unbiased sampling, like at least not in a way that is representative of the data set. And so like we're not blind to that, and we figured all of that out. And now we can take this like a subset of the data back to NumPy and pandas, and then work with any like Python library that we have and want to work with. And so what we're doing here is we're getting all the absorbent rides, which is what I've been defining here as like ones with a z-score greater than 2, and then converting that to pandas, like pulling this all back to pandas side, so we can work with that in pandas rather than Arkouda itself. And so, yeah, just printing that out here, like the first 5 rows in that column, like we'll see if we inspect these a little bit more, you'll see like the average mean here, fare mean was here. Man, I should have, okay, here's a good look. So this person paid about twice as much of the ride there. The average fare was $16. This person paid $35. Here's the average dollars, about 10. This person paid $30. So we're just pulling out like an interesting subset of the data so we can inspect that with our typical data science tools in the Python ecosystem. And so what we've done here is we're looking at the absolute worst fare z-score of all of this data set, and then printing that out. And so what we see here is this person rode from East Harlem North to East Harlem South. The average fare from this ride is $10. They traveled 4.7 miles and paid $42. So this person paid or like about $10 a mile, which puts into perspective that $40 a mile, and about 4 times the average rate, $42 versus $10. So this is the person who I would say got the absolute worst ride cost of anybody in the entire New York City taxi cab set in all of January 2024. So just some of the interesting things you can learn with data science is who got the worst ride in all of taxi cabs. Yeah. All right. So this last point here, this last exercise that I'm not going to be able to walk through since our code space was rudely taken away from us, is this discovery exercise. And so now it's like, now is the question of like turning the table back on your hand. Like, is there anything more you want to explore in this data set? Like maybe you could check out the rides with a large number of people. Maybe you could check out like who tipped well, like what kind of is the common themes of like tips, if there's anything that led to more tips or less tips. You could also look into like the longest ride. Like it would be interesting to see if the very longest ride of this would be that guy who paid $1,400 for his ride. Like, was that the longest ride? Did somebody else ride longer? Like, the possibilities are endless here. You know what I'm saying? Like, we are the explorers as data scientists today with these tools in our hands. So the possibilities are endless. All kinds of uncovery and discovery to happen with Arkouda. And yeah, so I hope you all take some time to discover from this data set a little bit more and potentially some other data sets that you are working with outside of the New York City taxi cab data. And then, okay, so the last few things we'll talk about here is this ability to disconnect or shut down from the server from the client side. If you disconnect, this will just like unpair your client from your server. If you shut down, this will kill the server for everyone connected to that server and will shut down that server in its entirety. And so I've got some notes here on where you can download the data from this data sets, and you can also find some of the other New York City taxi cab data sets if you want to expand your horizons here on what kind of data you're analyzing here. And the last thing I want to mention here is just running Arkouda at scale. So like in this tutorial, we ran Arkouda in a code space, which is kind of like this shared marine machine resources provided by GitHub. So you're not really getting what Arkouda has to offer. You're not having like this large scalable distributed server. And so if you want to get Arkouda running on a distributed machine, you'll need to build Arkouda from source and launch on that machine where you can then connect to that running server from the client side. And so we have some installation instructions for how you can get Arkouda set up here in the Arkouda GitHub repository, where we have some documentation for that. And so this is where I recommend to come, the Arkouda documentation website, to learn more. There'll be a link to that in the description as well. And so, yeah, so I think that was pretty much the last thing I wanted to say. Oh, we also have some Arkouda Docker images that you can find, and there'll be a link to that as in the description as well. And so, okay, I think that was the end of the talking that I had planned for you all today. So we made it through. No more suffering through that, my stumbling through this tutorial, but I hope you all learned something, and we'll be able to get some real life value out of Arkouda and what Arkouda has to offer. And I guess the last thing I'll say is like you can reach out to the like both Chapel and Arkouda have GitHub projects where you can open some issues and communicate with the team. And we're also very active on Gitter, which is one of our communication platforms. If any of you are familiar with that, like please find us there, ask some questions. We'll be happy to help. So that's the favorite part of my favorite part of the job, is getting to work with people who are trying to get started with Arkouda and actually use Arkouda on real problems. So definitely please ask us some questions about what you're trying to do with Arkouda. All right, that's all I've got for you. Thank you.